So I've prepared the tutorial for today, and it seems to me that there is a lot of material. I mean, I couldn't prepare the whole thing in 1 hour myself. There was a lot of calculation also. I made a mistake along the way, which eventually delayed me quite some. Again, the plan for today is B1 and B2, but I will not cover the whole thing. The calculations are far too long, and there's a lot of tricks in there that I would want to actually explain, which to me the explanation is more important than the technique itself. So I'll try to see if I can get to them. So with further ado, I need to share my screen, and that goes from this button here. Can you see my screen? Can someone tell me if you can see my screen? Yeah, excellent. Thanks, Hannah. So I'll be doing like last week. Unfortunately, same hardware, so same software as well. So I'll be switching to here's my screen. I cannot zoom in, so I'll ask you to zoom in. And if you have any questions, please interrupt me via the chat. And if I don't acknowledge that there has been a question, then turn on your microphone and ask it. I've just calibrated my microphone and I should be able to hear you easily. Yeah, do interrupt me, please. Don't let me do a one-man show like last week. It's quite feels lonely. Okay, so we're dealing today with the example sheet number 3, and I'll start with B1, which seems to me that it's the problem that has the most value in a mathematical course. So what we're dealing with here is a concept that is very important in a lot of different aspects of mathematics. It's got a lot of to generate bases and generate bases in a lot of contexts. I've just been working yesterday evening and this morning on a numerics problem where effectively I have to create the basis of functions. These functions have to be orthonormal. They have to be and they have to generate a space of solutions, right? So we need to be very careful. And one of the things that we do when we have when we try to generate these functions is to apply a Gram-Schmidt decomposition to make sure that none of these functions projects onto another, to make sure that each function contains as much information as possible and there's no duplication of information between these functions. So let's have a look at what this problem is. So we're looking at the inner product. So let's consider the inner product. And this product is defined as follows between so you have to always define an interval of existence of your or definition of your functions. And here we're going to say that it's -1, 1 included. And this inner product is written like this. There's various notation, but this is the notation that I understand we're using in this course. So the two functions separated by a comma and surrounded by parentheses. And what we're doing here is the integral, and an inner product is always going to be an integral. Okay, it's a product of continuous function, therefore it's an integral. So it's over the domain. It's a product, so you always end up having to multiply one function by another. And typically what happens is you can stop there, right? And that's an inner product. That's a completely legitimate inner product. But most of the time, and to gain in generality, you add another function, which is typically called a weight function or something like this. And in this case here, we're adding a function x plus 1. And the idea there is that we are not weighing the product of these two functions in this interval in the same way everywhere. Okay, so what this means is that, well, the greater x in this interval, the more the product of these functions is important. Okay, and reversely, the lower x is, the less important this is. In fact, for x equals -1, it doesn't matter. Okay, so this is the point. There's this weight function, and what we say is that we want these functions to be orthogonal. If we say these functions are orthogonal, it means that based on this inner product, it means that this integral with this weight here is equal to 0. That's what orthogonal functions mean. Okay, they have to be defined with a certain inner product. The same way you take two vectors and you say they're orthogonal, you take the dot product, and then when the dot product is 0, well, that means that they're orthogonal. That's the same thing here, except that it's no longer a dot product, it's an integral of the domain of definition, and you multiply it by wave function. Okay, so we've got this. And what we're saying is that we're considering a basis of function, which is a polynomial a set of polynomials, right? Which is 1, x, x squared, x cubed, etc. And what we're saying here is what we want you to do is to make this is a basis of function. And what we want is to make it orthonormal, right? Make it orthonormal. And orthonormal means, as I said, ortho means that each of these functions are orthogonal with respect to each other. And normal means that they have a unit norm, okay? And orthogonal and normal imply that you're using an inner product. It implies a norm. The norm is sort of defined through this inner product here, okay? So we need to specify that we need to make this basis orthonormal with respect to a certain inner product. And that's the inner product that we've defined. Okay, so orthonormal with respect to the above inner product. So you see what I've done there. I'm emphasizing that if you say functions are orthonormal on itself, it means nothing, because you haven't told us what the inner product is, the norm that you're comparing these functions with. Okay, so that's the key thing here. Okay, so let's do this. And the way we do this generally is via a process that is called the Gram-Schmidt decomposition of these functions. And so let's just do it in a simple way. Let's just make sure that we have orthogonal functions first. Okay, we want orthogonal first, then we will normalize. Can I make sure that you guys are listening to me, that there's no issues, no technical issues? Can you just very quickly confirm? Otherwise, I'm kind of, it's always worrisome. I've had one experience 2 years ago. Oh, good, excellent, thanks, Luke. I had an experience 2 years ago where I did half an hour of lecturing, and actually I was offline. So I don't want to do that again, especially when I'm struggling so much to breathe and talk. Okay, so we want these guys to be orthogonal first, and then we'll worry about the rest after. So these functions, they're just the monomials, right? The 1x, x squared, x cubed. So let's have a look at what the inner product for these monomials. Inner product of monomials. And what we get is we're writing down x to a certain power n times x to a certain power m between parentheses. So we're really doing that inner product, right? And so if I replace these in my integral, I get x to the n plus m, okay, times x plus 1 dx. That's what I get. I can integrate this very easily. Well, I can just distribute this easily. N plus m plus 1 plus x n plus m dx. Putting parentheses there to make sure that we understand that dx applies to everything. And we can also very simply integrate that stuff. So that gives me x to the n plus m plus 2 over n plus m plus 2 taken between minus 1 and 1. Here I get x to the n plus m plus 1 divided by n plus m plus 1 minus 1 and 1. Okay, so that's very simply my integral. And now we see that when we have the upper bound of these integrals is 1, so what that means is that the first term of each of these boundary terms, right, of these each of these integrals is going to be 1 to a certain power, which doesn't matter, divided by a certain number. Cool. And the second term is -1, so it's going to be -1 to a certain power, right? And if that certain power is odd, that remains -1. And so we get 1 minus -1, which is 1 plus 1. That's great. But if that power is even, we get 1 minus 1, which is 0, and nothing comes out of it. So it's important here to identify whether n plus m plus 2 here is odd or even, and whether n plus m plus 1 is odd or even. So obviously, if one is odd, then the other is even, and vice versa. Okay? Is there a comment? I can hear someone saying something. No? Okay. So so this is what we're looking at, right? We need to figure out whether something is one of these is odd or one of these is even. So if n plus m is odd, then we know that yeah, I'll put black. If n plus m is odd, this number here is going to be odd, right? Sorry, odd. Sorry, odd. This number here is going to be, yes, odd. Sorry, it's going to be odd, and so this integral here is going to be equal to 2 over n plus m plus 2, and the other one is equal to 0 automatically because n plus 1 is even. So what we have is two cases. We have one case where n plus m is odd, in which case this is going to be the first integral that is going to prevail, and it's going to give us 2 over n plus m plus 2. So that's if n plus m is odd. And if n plus n is even, then we're looking at the other integral, and we were going to have 2 divided by n plus m plus 1. Okay, if n plus m is even. Okay, so that's what we get here. And so, you know, we can have a look at what happens for specific, and that's going to be helpful for us in a moment. So for specific cases, say, for instance, I'm looking at 1, 1, the inner product between 1 and 1. The power is 0 and 0. So n plus m is even, 0 plus 0. And if n plus m is even, I'm looking at this case here. There's like 5-second delay between what I'm saying and the arrow. So I'm looking at this case here. N and m are 0, so I get 2. Okay, so that's 2. Then I can look at x1 and notice, you know, that our we can switch over the first and the second term. It's just a product. F times g is g times x, right? Times f, sorry. So so we can switch them over. So there is this operator is kind of commutative, and in this case, n is 1 and m is 0, vice versa. So the sum of them is odd. So we're in the first case, and the first case tells us that it's 2 divided by n plus 2. So that's 2 divided by 3. Okay, that's another case. Then we can look at x squared 1. And again, you can commute, right? You can change the order of these things. You can, sorry, permute these two functions. And so what you get there, if you write down the inner product between x2 and 1, now this time your n plus m is even. It's 2 plus 0. So you're in the second case. And you get 2 divided by 2 plus 0 plus 1. That's 2/3 as well. Okay? Then you can look at x and x. And the sum is 1 plus 1 is 2. It's even. So you get 2 divided by 1 plus 1 plus 1. That's 2/3. And you can keep going like this. Particularly, we're interested in x squared x, for which this time the sum n plus m is equal to 3. So we're on the odd case, and we get 2/5. Obviously, x squared is the same, and then we get x squared, which is going to give us even. And so we're in the bottom case. That's 2/5 as well. 2 divided by 2 plus 2 plus 1. And I think we need to go to x cubed, do we not? Yeah, let's go to the x cubed. So let's do x3, 1. So x3, 1 again, we're in an even case. The sum is 4, and we get 2/5. Then we have x cubed x squared. The sum is odd. Wait, did I say odd in the previous case? I meant even. Now the sum is odd, so it's 5. So we get 2/7. And the last term that we're interested in is x cubed. And now we have an even sum, and we get 2/7. Okay? Is that clear, this sort of preliminary calculation? Are there any questions? That looks all right. So what we do now is that we're going to proceed to this Gram-Schmidt decomposition, okay, or this Gram-Schmidt method, depending on how you want to call it. So Gram-Schmidt, and the point of Gram-Schmidt you'll see in a second. It's a very simple concept, and honestly, it looks potentially daunting when you look at it mathematically on the paper. But if you just remember the idea, you can reconstruct it without learning anything. It's that simple. So I'm going to consider my first vector, and again, you know, I don't worry about the fact that they're not normal at the moment. They are not of norm 1. So I'm going to consider my first vector, and I'm going to call it phi0. And phi0 was 1. Remember, I had that. So that's my starting point for this Gram-Schmidt decomposition. Then the first vector, besides this one, sorry, it's phi1. I'll call it phi1. Remember, it's x. I'm calling that a vector, but it's a function. It's because I'm used to talking about Gram-Schmidt decompositions in vectorial analysis. So I'm looking at this guy now, the second term, the second function, and the idea here is, well, I've got it, but remember what I want is to have it orthogonal. Normal, I'll take care of that later. But I want to have this function orthogonal to the first one. So I've got it, but I just need to take out the projection of that function on the first one, so that what remains is orthogonal, right? So I'm going to take out the projection. How do we project? Remember, vectors, we take a dot product, or we take an inner product when it comes to functions. So what we're going to take is the inner product between this and the first function. And this is going in the direction of that first function. And I want to subtract that. So I'm multiplying by that first function. But when I've done this with functions that are not normal, that do not have norm 1, right? In particular, if phi0 has norm 2, then I would have multiplied actually the projection by 4 here, because I have phi0 here times phi0 there, right? So I'm actually, the bigger phi0 is, the bigger this correction is. That doesn't make sense. We should not allow that. We should just take out the projection of x onto the direction x0, not multiplying by the size of x0 of phi0. So what we should be doing is dividing. Oh, oops, wrong button. So what we should be doing here is dividing by the norm of the stuff that's undesired in the denominator. And what's undesired is the norms coming from phi0 and phi0. So, well, let's just divide by phi0 the norm of phi0. That is to say, the inner product of phi0 by phi0 itself. So what we've done there essentially is we took x, and it's got some projection on 1 because of the definition of our inner product. It's more complicated than if the inner product was just 1, right? In which case there wouldn't be necessarily a projection. But there is a projection, and what we want to do is get rid of that projection, and we need to subtract from this x. We need to subtract that projection That projection is defined here. It's x times phi 0 defined by the inner product, and times that gives the amplitude defined by the inner product times phi 0 to carry the direction in functional space. But when we do this, the amplitude of phi 0 matters, and because the amplitude is not 1, we need to normalize that by the norm of phi 0. And that's why we divide by this. So that in the end, what we have is something in the second term that has an amplitude proportional to x only. Does that make sense? Can someone tell me if there's any difficulty there in this explanation? We're good. It's crucial. I mean, if you understand this expression, if you understand this explanation, the whole I'm sorry. If you understand this explanation, the whole concept of Gram-Schmidt decomposition becomes trivial, and you don't have to learn anything. Does that make sense? Luke, you're the spokesperson for the group. Does that make sense? It's going to regret saying all good. Okay, Luke has gone to sleep. Someone else tell me if that makes sense. Am I online? Hello? Okay, cool. Excellent. Thanks. Awesome. So let me just rewrite this clearly without all the scribbles that I used for the explanation. So again, we take x and we want to take out the projection of x on phi 0, which is defined like this, but that has a norm that is proportional to phi 0 squared. So I want to take this out. So I am essentially dividing by phi 0, phi 0. And similarly, if I want to continue, I'll explain that in a moment. Let me just calculate this. So I get x minus an x. The dot product, sorry, the inner product between x and phi 0, we've calculated that already. X and 1 is 2/3. It's up there. So we get 2/3 divided by phi 0, which is 1 and 1, which we had. It was 2 up there. So divided by 2 times phi 0 is 1. So that phi 1 becomes x minus 1/3. Okay? So that's phi 1. So we have phi 0 here, we have phi 1 here. And now I want to continue this process, right? So I'm going to do phi 2. And phi 2 is going to be it's x2. Remember, that's the second function, the third function that we were wanting to play with. So that's x2. And now, well, okay, but we want this guy to be orthogonal to all of the other vectors, functions that we've generated. So we need to have this orthogonal to phi 0 to start with. So that's x2 phi 0. Remember, it's exactly the same stuff that we're doing here. We're taking out the projection, right? But that guarantees it's going to be, that guarantees that the function that we're creating here is going to be orthogonal to phi 0. But what about phi 1? We need to do the same thing. So we're going to be doing minus x squared phi 1 divided by phi 1, phi 1, phi 1. Okay? And you can keep going like this. To get all your vectors like or your functions like this, and this is the idea. So you see, second term, the third function, you have to take that function and make sure it's orthogonal to the first two functions. The fourth function, you're going to have a third orthogonalizing term, and so on and so forth. So let's have a look at that. So that's x squared minus x squared 1, inner product between x squared and 1. That's 2/3. Okay. So we get minus 2/3. The dot product, sorry, the inner product between 1 and 1 was 2. And then that function phi 0 is 1. And then we get the inner product between x squared and phi 1. Well, that's a little bit more complicated. So that's going to be the inner product between, remember these inner products, they are, you can distribute it when you have a product in there. So f plus h dot product with g is f with g plus h with g, okay? So what we get here is x squared, and phi 1 was x minus 1/3. Sorry. So we get, first we get x divided by phi 1. Let me just actually decompose that. I'll just decompose that more slowly. Okay, so what we have here first, we need to determine what phi 1 is. Okay, that's that product. So phi 1 is going to be, remember phi 1 is this guy. So it's going to be x by x. Then we're going to have plus, let's just, yeah, okay, fine, I'll write it, plus 2x with 1/3, which is x with minus 1/3, which is x with minus 1/3 plus minus 1/3 with x, and plus minus 1/3 minus 1/3, okay? So what I get there is, obviously I get x with x, I get minus, I should write minus 2/3, x with 1, right? Because constants come out of this inner product. And then here I get plus 1/9 of 1 plus, and 1 inner product with 1. Okay, so I get all that. And then I just read out what these xx, x1, and 1 inner products are. X with x was, I think it's 2/3. Yeah. X with x is 2/3. And I get minus 2/3, that's 2/3 as well. And I get plus 1/9, and that's 2. So what I get is 2/3 minus 4/9 plus 2/9. So I get 4/9 in the end. So we got we just managed to get the numerator, the denominator, but we need to get the numerator there. So the numerator, that's x squared with phi 1, and I'm going to decompose it in the same fashion. With these calculations, again, I'm just trying to be doing a bit of meta advice there, not like the specific technical stuff. With these calculations, these are all extremely simple calculations, but they're very tedious. Do structure your work. Do not try to carry it out as I was starting in the beginning and just try and carry out the whole calculation in a block. Just make your preliminary calculations on a piece of paper in the corner, or say, you know, here we need preliminary calculations, and do these so that you only have trivial operations to do in the end. That's gonna limit the number or the risk of failure or the risk of miscalculation on your behalf when you do these calculations. So x squared x, and then I've got for the same as before, x squared 1. Okay, so this is with minus 1/3. And x squared x, I think, is 2/5. I remember. Well, yeah, it's 2/5. So I get 2/5 here minus 1/3, and I think that's 2/3, right? So in the end, I get 8/45. 2 9s, yeah, that's right. Okay, so that's what I get there. So if I plug everything together with the formula that I derived for phi2, I was getting x squared minus 2/3 divided by 2 times 1, which is the orthogonalization versus phi0, function 1. And then here what I get is, is there plus or minus? I don't remember actually. Minus here, yeah. Minus 8 divided by 45 divided by 4 divided by 9. And this is times phi1, which is x minus 1/3. So if I complete this calculation, I'll get phi2 equals x squared minus 1/3, minus 1/3. That stuff becomes 2/5, simplifying the 8 with the 4 and the 45 with the 9, times x, and I get 2/5, the minus and the minus, 2/5 times 1/3, that's 2/15. And so I can simplify this and get that it's x squared minus 2/5 of x plus minus 1/5. Okay, and that's phi2. Okay, so what we got there, and I'll stop at phi2. I think there's no need to go to phi3 in the text of the question. So what we have here is we have these three functions. Remember, they were one x and x squared, and we've normalized, and we've orthogonalized them with respect to each other based on the inner function, the inner product that we had to give us this set of polynomials. Okay, and these, if you take them, and if you take the inner product between, say, phi1 and phi2, or phi1 and phi0, or phi0 and phi2, you'll get 0. They're orthogonal. The last thing that we need to do is to normalize them, right? So we need to make them normal. So to normalize them, it's not that complicated. It's another simple step. We're going to call these vectors, these functions this time E0, E1, E2. And E0 is going to be the normalized version of phi0, phi0 divided by the norm of phi0, and that norm has to be defined in the same fashion as we've defined this inner product and as we orthogonalized these functions. That is to say that what we have here is that it's going to be phi0 divided by the square root of phi0, phi0. Okay, so if you remember, phi0 was 1, and phi0, the inner product was 2, so you take the square root of 2, and that gives you this first function. I don't like to have square root in the denominator, so I'm just multiplying by square root of 2, or square root of 2 divided by square root of 2 to get this equivalent. Okay, so that's for E0. Then you can do the same thing with E1. And E1 is, that's going to be phi1 divided by phi1 norm. And so the norm of phi1 with phi1, we've already calculated it. If I remember, where is it? Phi1, phi1. There we go. It's there. It's 4/9. It's this guy here. So it's 4/9. And we need to take the square root of 4/9. Fine. So the square root of 4/9 is 2/3, so I get 3/2 of phi1, which is 3/2 of x minus, it was, what was 1/3, right? So that's minus 1/2. It was 1/3. Yeah. Okay, so minus 1/2. So that's E0. That's E1. Guys, I'm really struggling with my throat right now. And then let's do E2. So E2, that's going to be phi2 divided by phi2. Okay. And phi2 by phi2, did we calculate this? No, we didn't. So we need to calculate it. Okay. So given the time, I'm not sure it's very good use of my time, but P2 was x squared minus 2/5 of x plus or minus 1/5. Yep. So you essentially, to do this calculation, you proceed in the same way as usual. You take each of the term individually, you take the coefficients out, and after some simplification, I need to get my sheet there. After some simplification, then you get the result, which is 8/75. Okay, so I'm just skipping this, but do it. It's again, it's a good technical exercise. So what we need to do is to take the square root of this. Okay, so square root of 1 over square root of P2. That's 75 over 8, which you can simplify by identifying the 25 in the numerator and the 4 in the denominator. So you get 5 over 2 square root of 3 divided by 2. And then you can, if you want to be fancy and not have a square root in the denominator, you can multiply everything by square root of 2 divided by 2. And you get 5/4 of square root of 6. So I'll do it. I'll manage. 15 minutes to hold. So what we get there is E2 is P2 divided by this guy. So it's P2 divided by square root of P2. That is to say 5/4 square root of 6 times x squared minus 2/5 x with minus 1/5. It's becoming difficult. Okay. So E2 equals 5 square root of 6 divided by 4 x squared minus square root of 6 divided by 2x minus square root of 6 divided by 4 minus square root of 6 divided by 4. And this is your second function. So what we've constructed there is a basis of orthonormal functions in your based on the function set 1x squared. Okay, and we've identified, we've calculated this basis of orthonormal functions based on the inner product that we've defined in the beginning, which is there. Okay, so you might think this is tedious, and certainly it is. I'm not denying that it's not tedious. But this, if you want a high-level perspective on this technique of Gram-Schmidt decomposition is something that we do in numerics. And I'm just going to give you an example. This is a code. I don't know if you can see this. This is a code I was working on yesterday and this morning. And if I go, oops, no, I don't want to do this. If I go to this page there, you can see somewhere, I'm pretty sure I've got a Gram-Schmidt decomposition. There you go. And you can see that at some point I generate a set of functions, and what I'm doing is a Gram-Schmidt projection of these functions. There, you can see it. It's in there. And that Gram-Schmidt decomposition, all that tedious calculation that you do, that we've just done by hand, which took us 45 minutes, is just some nested loops like this. It's fairly straightforward. It's 10 lines of code. And so it takes no time for a computer to do this. It takes you a lot of time, but it's important for you to understand what is happening when you do it. Because then you would be potentially using these types of tools in more advanced scientific areas, which will effectively actually not be a technical difficulty or not even a challenge. You see what I mean? Are there any questions on this Gram-Schmidt decomposition? Oh, how do you split the inner products like that? Oh, Luke, can you tell me what you were referring to? Which part of the question? Sorry, I didn't see that you had written something. You should have turned on the microphone and said something. Which part of the question? Or the calculation, should I say? When you change from phi to x, phi, which phi? Okay, wait. Oh, is this for the x squared phi 1? Ah, okay, let me just show you. Okay. So this is this calculation you're referring to. So I've got x squared phi 1, which is x squared, and phi 1, if my memory serves me well, is x minus 1/3. Can you confirm to me that's the calculation that you're referring to? Yeah, okay, cool. So that's what I have, but you can distribute these products, these inner products. The way it's defined, you can distribute it. It's not a convolution product where, you can't. This is defined as the product of two functions. So what that means is that here I've got x squared x, and I've got plus x squared minus 1/3. Okay, and well, similarly, I can take out the constants, the multiplicative constant. So I get x squared x plus, minus 1/3 x squared 1. Sorry, separate this. And then these guys, we already know them, right? This is 2/5, and this is I think 2/3. Does that answer? Cool. Can you confirm to me, or at least someone confirm to me, that this is clear, this Gram-Schmidt decomposition? It is tedious. Learning it is tedious, but the concept is extremely simple and it's very applicable. It's extremely powerful. Okay, cool. Thanks, Hannah. Again, if there is any question, do let me know. Okay, so let's have a look at what the second part of the question was. So yeah, I'm not going to do these calculations, or where am I? Because it's the same stuff over. Can I do? Okay, I'll try and cover, and sort of high level, give you some advice or guidance for these questions. So find the best in the mean approximation. A0 plus A1x plus A2x squared of f equals x cubed, based on what we've just done, right? So based on these functions that we had and the inner product that we had. So you realize that x cubed, you cannot have it, because you've truncated with E0, E1, E2, or E0, E1, E2, you've truncated before x cubed. So you cannot actually represent it exactly, but you can always approximate it. So let's do that. So the way you do this is actually very simple. You're just projecting. Again, you're projecting against your vector. So you're going to say that A0 plus A1x plus A2x x squared, and you're going to say that this is a projection, and how you project. Same as when you do a Gram-Schmidt decomposition. The idea is we project. So you're going to be doing a projection of f, that function that you want to approximate, on on phi0, and you're going to be giving that in the direction of phi0. But again, if I take phi 0, there's a norm, and I don't want that norm to bother me. So I have to divide by phi 0, phi 0. And similarly, then you get f phi 1 in the direction phi 1, you have to divide by phi 1, phi 1. And then you get f phi 2 in the direction phi 2 divided by the norm of phi 2. Note that I've decided to do it like this because it's simpler in the calculation. But there's perhaps more elegant mathematically. By using the fact that you've already normalized these vectors, you could have just written f e0 plus f e1 plus f e2 e2. Essentially, you're taking the projection of f on e0 and you plug that in the direction e0. You add to that the projection of f onto e1, plug that in the direction e1, and you add to that the same stuff for e2. Simple. And that works here because e0, e1, and e2 are normalized. e0 not being normalized, it appears twice in the numerator, so that you have to divide it by twice. That's the inner product. And the same thing goes when you do the Gram-Schmidt decomposition. Say you normalize immediately E0, right? Immediately you get phi0. Immediately you get E0. Then when you do your Gram-Schmidt decomposition, you can immediately write instead of that stuff for phi1, you can write E1 equals actually can we? No, you can't. So I'll shut up there. I'll shut up there. So that's very simply that calculation that we ask you to carry out. So it's quite straightforward. I'm not gonna develop it. It's simple enough. Once you've done the previous calculation, and I've already given you the products here, the inner products with x cubed here. So you just essentially have to do the same game as I've just done. You just plug them in and you solve. But I want to say a few words, and I don't have enough time to do that, but I will try to do my best to structure my thoughts about B2. So B2 is a simple one-liner question, and these are the most dangerous ones. Find the Fourier expansion of a function that we defined as f of x equals minus x for minus 1 x 0 and x squared for 0 x 1. So you're looking at a function that looks like this, right? Minus x, that's something like this, and then x squared, so that's something like this. Okay, between minus 1, 0, 1. I'm not drawing well because I'm trying to go fast. Do not take example of me and write correctly at your exam. I would take marks off what I'm writing there. What we're doing here is looking at the Fourier expansion for this. So what we need to do is that Fourier expansion, we need to write it down. So that's f of x, and typically what we get is a 0 divided by 2 plus the sum for n equals 1 to infinity of, and we get Fourier expansion, so we get cosines and sines. So we get an cos n pi x plus bn sine n pi x. Okay, this is our cosine and sine expansion, our Fourier expansion. So the way we solve for this is straightforward. Projection. The way we project, and there is no here there is no inner product that is specified. We take the basic in the inner product with weight 1. So a0 is going to be the integral from -1 to 1 of f of x dx. Okay, and if you solve this, and I'm going to go quickly on this, right? You need to split the integral between -1, 0, and then 0 and 1, and you get 5/6. That's not where it's technically difficult. Where it's technically difficult is the other guys. So you get an, and the definition is -1 to 1 of f of x cos n pi x dx. You take f and you project it on cos n pi x. Why? Because that would give you an. If fx is proportional to cos q pi x, q being different from n, that integral is always going to be 0. So it's fairly straightforward. It projects immediately. So because the cos and the sine are orthogonal with each other based on the inner products defined as this, fg dx, okay? The cos, all the Fourier functions, all the trigonometric functions are orthogonal with each other based on this inner product. That's a fact that is that you should have shown, you should have demonstrated at some point in the lecture. So that's the definition for an, and you will find that this comes down to -1, 0 minus x cos n pi x dx plus 0, 1 x squared cos n pi x dx. And similarly for bn, in a similar fashion, you get the same stuff, but with the signs instead of the cosines, right? -1, 0 minus x cos, sine n pi x dx plus, I'm trying to rush because I've got a meeting as well, sine n pi x dx. Okay, so you've got the same structure there. And the key thing is, what's the integral? Keep it general. Keep these a sub n and b sub n. You don't want to be specific because you want to have all the information, and you can have it. And so the key thing here to notice is that if you define a function Cn, which is integral, and I'm not putting boundaries of integral here, x to the power n cos ax dx, and you integrate this by parts, you get something, right? And that something is, and if you do the same thing for Sn, which is the same integral but for sine, so you see I'm doing the x for the c for cosine and the s for sine, then this integral writes xn sine ax over over a minus n over a times Sn minus 1. Okay, and similarly, if you look at the other, you get x to the n cos ax over a plus n over a Cn minus 1, and you get the recurrence relationship for these functions. And so you can solve for these functions. Well, what matters in the end is what you see here when you define them, is that these n's there, in the integral that you're interested in, they're only either 1, you can see I'm writing it in red, or 2. So the only terms that you care about is C1, C2, S1, S2. Okay? So then the only thing that you need to do in this question, there's a number of tricks, but that should guide you quite well, is you need to calculate C1, C2, S1, S2. Okay? And that will give you the AN, BN when you apply the boundaries of integration. Okay. All right. So that's all I've got to say. It's a very long question, B2. Technically very interesting, very interesting technically. Have a look at it. Try and work hard on it. This is very interesting to improve your technique. but it doesn't have as much content, mathematical content, as the Gram-Schmidt one in B1. Okay, that's me. Are there any questions? If not, then I'll see you next week, and I'll be at the university, and I don't think that there will be any problem next week. So I'll see you in LT3 next week, Friday, 1 p.m.